This may happen because your telephone can work in Korea, in Seoul, where it's still winter now, unfortunately, -1 or -2, and but also in Arabia, where it's 60 degrees. So if this material is not working above 50 degrees, it's a problem to use in a battery. But it is environmentally compatible and is based on low-cost components. And I don't know if I wrote that. No. And I forgot to write here that there are ways to establish the structure. So there are some possibility to modify, slightly modify the composition of lithium manganese oxide, maybe by adding some external component like cobalt, aluminum, and so forth, and destabilize the structure. So there is no any more distortion, so there is no any more release of manganese. So this is why now some industries are using them. This material is using this material. And if you want to have more information on this is in the lab of Professor Sun. This work is carried out now. I think, I don't know who of you is doing that, but I understand that one way to prevent dissolution of manganese is having the manganese particles covered by carbon. You see, this carbon coverage is thin enough to allow lithium in and out from the material, but it protects. It's thick enough to avoid manganese to go out. Okay? I think Boram, you are doing this work? Where is Boram? Oh, you are doing this work? Are you the one doing the work on coating lithium manganese oxide here in the Sun Lab? Okay. So by this way, it's possible now to use this lithium manganese oxide as a cathode, and this is a good achievement, of course. Now let's talk about lithium iron phosphate. It's very good material because theoretically has a lot of interesting features. The structure of this material is the olivine structure. We can very simply discuss in terms of distorted hexagonal close-packing oxygen framework. This is the oxygen. See? This is the purple is the framework. And this framework contains lithium ions. Here they are, and also iron ions. And this creates a series of channels where lithium can move. You can see the channel very easily here. This is the channel form, and this lithium can move in and out. Okay? What is the electrochemical process here? The electrochemical, again, remember that we are talking about cathodes. So the material, cathodes. So the material have to be able, all the cathodes have to be able to give lithium. Okay? So here, lithium is removed all the way to form this compound. And then it can go back. And you see that in this way, we actually pass from one phase which is called triphyllite, which is this, okay, to the other phase, which is called heterosite. So both of them are occurring in nature. You see some pictures here. So this is a two-phase process, and when we have an electrochemical process which is formed by the coexistence of two phases, we always have very flat voltage. Okay? So you see here that when we remove lithium and we go from this phase to this phase, namely we pass from iron 2 to iron 3, okay, we have a very stable voltage, which is about 3.5. Okay? Then here the process is completed at about 170. This will be less because this is a practical capacity, not a theoretical capacity. Then we can charge it back, going in the same direction. However, this is all these give us a lot of interesting features. These materials are abundant in nature, so this doesn't cost too much. The voltage is very flat, so sometimes you need a flat voltage for a battery to maintain constant the voltage. And of course, iron is also compatible. You can eat iron. Yes, you can eat iron from spinach, like with the guy of the cartoon eating spinach. Who was the guy? Popeye. That's right. Popeye. However, there are problems here. And the main problems is that the electronic resistance of this and this is very low, very high. And you remember that when we have a generical cathode, C, whatever, and if this cathode releases a lithium ion, also lithium electrons have to go. Also electrons have to move. So for a good cathode material, we need high lithium ion conductivity, so low resistivity, and also high electrons conductivity. And these have to be combined. Okay? Why is that? Because remember that if we are talking about rate of discharge, okay, charge and discharge, this rate is directly connected to the number, to this aspect, because you remember the rate is current, okay? So current is related to the number of electrons. The number of electrons are related to the numbers of lithium ion. So if you want to have a rate of 2, maybe if you have 1 electron going out, the current is one value. If you want to have a higher value, the electrons must be 2, 3, 4, 5, 6, 7, 100, 1 million. So you need a very high, very fast movement of electron ions. Otherwise, the rate is not good. So rate is very important for some applications of these materials. For instance, this lithium iron phosphate is now considered to be a good cathode material for lithium batteries driving a car, okay, an electric car or a hybrid car. And if you have an electric car and you're driving on the street and you want to bypass another car, you have to accelerate. And to accelerate, you need more current in your engine. So the rate is very important. And if you use lithium iron phosphate as it comes from nature, this rate is very low. And this car will be much wider because you have a lot of ohmic overvoltage. So how can you solve this problem? Again, with an approach like this one. You see that the most common way of making this electrode useful is as indicated in this very high resolution TM picture. You see that here in this picture you can even see the layer of lithium iron phosphate. And you see that this material is coated by carbon. This is 20 nanometer. So I would say that this is maybe maximum 5 nanometer, maybe 3 nanometer. So this give you the condition, as I told you before, that this carbon coating is very, very thin. But why? What is the reason for making this carbon coating? Well, suppose that we have a normal situation in which you have particles of lithium iron sulfide like this. Lithium iron phosphide like this. As I told you, since we have a very high, very low electronic conductivity, maybe this part is not in contact with this, because here we don't have enough conductivity. Suppose that this part is only contacted by this point here. Okay? The conductivity is not enough to utilize both of them. So we lose part of this material by losing conductivity. However, if we have the same situation now, we carbon coated, you understand now that all the particles now are electrically connected one to each other because of this carbon contact, because carbon is very good conductor. Okay? You know by now. So the production of lithium iron phosphide for practical application requires all this type of modifications. Not only this one, but also maybe to some doping to improve the inherent electronic conductivity and so forth. And this is the reason of the legal dispute which goes around in the world, because, especially in the United States, because each company claims to have the best way to do that. And they want to protect that. So if we compare now again the properties of lithium iron phosphate with respect to lithium cobalt oxide, you see that we have some issues, some drawback. So the voltage of lithium iron phosphate is 3.5 volts. Instead of